I'm Bob Duhamel. Today I'm going to talk about voltage in a loop when current is induced by a changing magnetic field. This isn't something you'll come across every day as an electronics technician or electrical engineer, but it will solidify your knowledge base and help you with circuit analysis. So let's get started. The scenario is that I have a coil of wire and some kind of a changing power source. This could be as simple as a battery and a switch, which is used sometimes to analyze this particular scenario, or this could simply be an AC current source. The analysis isn't really going to change because we're going to look at a particular moment in time as we analyze this circuit. So let's just say we have a changing magnetic field. I guess I'll leave the AC current source here for now. So we have a changing current, therefore we have a changing magnetic field. The magnetic field is getting stronger and weaker, reversing polarity, getting stronger and weaker. What we're going to do is take a look at a particular moment in time. So what happens is as the magnetic field gets stronger or gets weaker, there is an electric field around this coil that tends to want to make any electrons around it go in a circular path. To show that, I'm going to have to reorient this. So I'm going to erase this and show it from a different orientation so I can explain what we are going to look at here. So this is looking down on that coil of wire. So now it's going in and out of the board. We have our wires going to it that are inducing the currents and causing the magnetic field. And let's say that right now, because of the direction of the turns of the coil and the direction of current in them, and the fact that the magnetic field is building with a certain polarity, that at this moment in time, we have an electric field that wants to cause electrons to move in a circular path that is going clockwise. And at this particular moment in time, that electrical field has a total of, let's say for convenience, 10 volts. So that means there's a total of 10 volts in this field, and we'll see how that works out in a couple of moments. So what's going to happen if we put a loop of wire around there? So we're going to remove this arrow showing the direction of the electric field and replace it with another circle that represents a simple loop of wire. I'm showing this loop as a circle, but it doesn't have to be a perfect circle. Everything will still work the same, all other things being equal. And let's say this loop of wire has 10 ohms of resistance. Now, how are we going to analyze what's going on in this loop of wire? First of all, what do we have here? It's simply the secondary of a transformer. So if you don't understand transformers, I'll link my video on transformers in the description below. But as that changing magnetic field affects this loop of wire, it's going to induce current. Sometimes the current will go clockwise, sometimes it'll go counterclockwise. So how do we analyze what's going on there? First of all, if we take a voltmeter, I'll pull up my little red pin here to represent the red lead of a voltmeter, and let's say we put the red lead here and the black lead here at a couple of arbitrary points. What voltage am I going to measure there? Think about that for a second. We have a total of 10 volts. Let's see, I probably have about 5 volts. I'd say about 3 volts? Actually, you will measure 0. No matter where you put the probes of your voltmeter around this loop, assuming that the resistance in this loop is uniform, you will read 0 volts. Well, so how do we analyze this and why is that happening? Well, let's take a closer look. So we have a loop of wire and has a total of 10 ohms and a total of 10 volts being induced in here. So let's take just a section of that wire. Let's take, I'm trying to make that 1/10 of our total loop. I'm probably not perfect, but we can work with that. I'm just going to take a look at that one little bit of wire. So let's erase the rest of it and let's see what's going on there. So what's happening is we have a time-changing magnetic field. At this point, it's inducing a 10 volts in this entire circle, but this is only 1/10 of the circle, so I expect that to have about 1 volt in it. Can I put a voltmeter in there and measure that? Well, I just said I can't. I can put a voltmeter there. I'm still going to measure 0 volts, and I'll explain why in a moment. And we also have 1 ohm of resistance. So how do we analyze that little section of wire? We've already said that if I put a voltmeter across there, I'm going to read 0. So how do I analyze this? The key to analyzing this is understanding what Georg Ohm himself discovered when developing Ohm's law. We are imparting energy into the circuit. The magnetic field is coming from the center coil that's imparting energy into the circuit, so we have a power source here. It's the secondary of a transformer. So whenever you have a power source, any resistance in that power source must be analyzed in series with the voltage. Now we have the resistance along the whole section and we have the voltage across the whole section, but we have to analyze the voltage in series with the resistance. Let me explain why that makes sense. Let's just make that section of wire bigger. I'll make it straight here just to help us analyze it. And we have no magnetic field doing anything right now, so we have a number of free electrons I will represent with some dots through here. And if we try to measure the voltage across there, let's put a voltmeter here. There's the negative probe, and here's the positive probe. And what does a voltmeter measure? It measures the difference between two voltages. There's no such thing as an absolute voltage, so I can only tell what the difference is. And the meter's designed in such a way that if the voltage to the red probe is more positive than the voltage to the black probe, that we get a positive reading. Now, I prefer to consider a positive voltage as a higher voltage than a negative voltage. That makes sense. So if the red lead is at a higher voltage, we get a positive reading. If the red lead is at a lower voltage, we get a negative reading. So these electrons are pretty much like air molecules in a soda straw or whatever, which I often use as a demonstration of how a wire works. They're just floating around there freely and they're not bunched up anywhere. We aren't pushing them to one place and forcing them into a corner or anything where they will want to push back, where we will build up any kind of pressure. So there really is no difference in pressure from one end to the other, or difference in voltage. Remember, voltage is electrical pressure. So I expect this voltmeter at this point to read 0 volts. Okay, now let's put something in this wire that wants to push the electrons one way or the other. So how could I do this? Well, Georg Ohm used a thermocouple. His apparatus that developed his voltage was actually two dissimilar metals bonded together, and that caused a voltage which tended to push the electrons to one side. But in this case, we're using a changing magnetic field. Same exact effect. So what's going to happen? That changing magnetic field is going to want to push the electrons one way. So let's just erase most of these and show them bunching up down at this end, and there's going to be fewer electrons at the other end. So we've got a bunching up there. They're being forced that way. So let's say the magnetic field is pushing the electrons here so that the voltage here is 1 volt more negative than the voltage there. I really hate using that kind of terminology, but when we're following the electrons, we really have to. So basically right now I have a 1 volt difference. Now, I don't like using electron flow because you have to start using terms like more negative, more positive, and it gets a little confusing, which is why almost everybody uses conventional flow. So I'm going to change things around a little bit here and say, well, this magnetic field is pushing our electrons this way, but what happens when the electrons go that way? We have positive charges that are left behind. Now, these positive charges, although they don't move, for all intents and purposes, it looks like they do. So there's more negative charge over here, and the positive charges appear bunched up over here. So I'll just go ahead and just draw some red dots over here and a fewer here. So now I can look at this, that what's happening is that magnetic field is pushing our charges apart. It's forcing positive charges to go this way and negative charges to go that way, such that there's a 1 volt difference now. And remember, we have 1 ohm of resistance in that wire. Now, one thing that tends to confuse some people is they look at this and they say, hey, wait a second, I have 1 volt and 1 ohm. Shouldn't I have 1 amp of current flowing from, well, the electrons are going that way, positive charges are going that way. I'm going to try to stick to conventional flow, so shouldn't I have 1 amp of current flowing in that direction from positive to negative? No, because the magnetic field is what's forcing us to have this voltage. It's pushing those charges apart and not allowing them to flow back together. So even though we have a volt here and only 1 ohm, that volt is pushing electrons and positive charges away from each other, not towards each other. If we remove that magnetic field, of course, they will all just come back together and equalize again. So that is why you can have a low resistance and have voltage across a wire, but yet have no current, because this is a power source, and the power source is forcing the charges apart from each other. They cannot flow together. I'm going to redraw this a little bit because I want to get away from the electrons and go back to our typical conventional flow model that we use in this class, just like almost everybody else. So I'm going to just use the red to represent positive charges that are bunched up over this way and fewer down here. So there's our charges bunched up. We put our voltmeter here and here. We see 1 volt, positive to negative, and we have 1 ohm of resistance. Now what I'm going to do is take a wire over here, and I'm going to put another, for what it's worth, let's make this a 9 ohm resistor, because we can get some nice easy numbers to work with there. So now we have a total of 1 volt and 9 ohms. How much current should we have with 1 volt and 9 ohms? So with 1 volt and 9 ohms, we should have a current flowing here of 0.11 amps. So let's put a current meter in there and see what's really happening here. There's a current meter, and it reads 0.10 amps. So what's going on there? We have actually a little less current than we expect. Well, the current is not only flowing through this 9 ohm resistor here, but it's flowing in this loop and has to also flow through the 1 ohm of our current source here. So we have to add this 1 ohm to that 9 ohms, so we have a total of 9 plus 1 equals 10 ohms. So now 10 ohms goes into 1 volt, gives us 0.10 amps, and now it works together. So the resistance in our power source must be placed in series with the resistance over here. And this is the crucial discovery that Georg Ohm made that made it possible for him to develop Ohm's law, because others who had come before him were getting the same problem here. We're not getting the voltages and currents to work with our resistance. They, of course, were using different measurements, and they were using different lengths of wire, but still, they weren't getting numbers that were linear. Ohm discovered that you need to take the resistance in your source, in his case just a thermocouple, here it's just a piece of wire, and put that in series with your load. So when we analyze a power source, such as this piece of wire is, why is it a power source? Because there's a changing magnetic field that is inducing current in there. We now have to put the resistance of that power source where? In series with the voltage. So let's analyze this properly. So this piece of wire over here that is having current induced by the magnetic field looks like a battery with a resistor in series with the battery. Then we have our other resistor over here. So that is why we have to model a power source, even though the resistance is continuous along the power source, and even though the voltage is continuous along the power source, we have to model it with the voltage in series with the resistance, because of what I just showed, that the resistance has to go in series with this, and then we see the calculations work. So that turns out to be 1 volt, 1 ohm, and then again 9 ohms over here. So what do we get? We have a total of 10 ohms and a total of 1 volt, giving us a total current of 0.1 amps in that one little section of wire. So now let's put that back in our loop. Here is our coil that's inducing the current. Here is that little section. And now we know that that looks like a 1 volt battery with a 1 ohm resistance in series. So what did we have before? We had this complete loop. And so one section of wire looks like a 1 ohm resistor and a 1 volt battery. The next section looks the same. I'll just draw a little equal sign there so I don't have to draw the whole thing. So that loop of wire acts like how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, it's not even, but you get the picture. It acts like 10 little lengths of wire. Each little length of wire consists of a 1 volt battery and a 1 ohm resistor. So I have 10 1 volt batteries and 10 1 ohm resistors in the loop. Now, is 10 a magic number? No, I could have made this 100.1 volt batteries with 100.1 ohm resistors and had it much more finely divided, or 1,000, or maybe even 1,000,000. We can divide it as small as we want to, but even 10 is a little much for the space I have here on the board. Maybe I should have done 6 or something like that, but 10 gives us nice even numbers. So we can take that loop and break it up into sections, each section being a battery with a resistor in series. So now I'll just draw a couple more here just to give us an idea of what we're looking at. In fact, let's redraw this and get those spokes out of there to unconfuse it if we can. There's our coil, there's our loop. The loop consists of a battery and a resistor, and another battery and another resistor, and we just continue this all the way around. In this case, we broke it into 10 pieces, so it's 10 1 volt batteries and 10 1 ohm resistors in a loop. Now let's see how we analyze that. I'm going to break that down a little further. I'm going to use a fewer parts. What I'm going to do now is just use 4 batteries and 4 resistors. So there's 1 battery and 1 resistor. I'm going to make kind of a square loop out of this, and we'll analyze this and see what happens. Same idea, just different numbers here. And let's make each of these, just to stick with what we're doing, let's make each of these 1 volt and 1 ohm. 1 volt and 1 ohm. 1 volt, 1 ohm. 1 volt and 1 ohm. Now let's see what happens in this loop. So once again, we have that solenoid that has the changing magnetic field, which is inducing the current, and that means that this is a wire with now 4 ohms of resistance, and at this particular point in time we have 4 volts of voltage induced in it, causing our current to flow. And now we're modeling that wire as the square loop. Does the square make anything different? No, it doesn't matter what the shape is. Circle is kind of convenient for what I'm doing now. The square is convenient, but the shape of that loop, around that coil, if here's the coil and the loop looks like that, that's fine. If the loop looks like this, nothing changes as long as nothing else changes. So here we go. Now what do we have here? We have 1, 2, 3, 4 volts. Total of 4 volts in this loop. And we have a total of 1, 2, 3, 4 ohms. So what is our current? 4 divided by 4 equals 1 amp. So we have 1 amp of current, conventional current, flowing positive to negative in the loop. Now let's take a look at each one of these legs. So I have 1 volt here. I'm just going to draw a couple of lines. And of course that's negative to positive. I'll draw that right there, negative to positive. What happens in this resistor? Well, how much current is flowing through it? Well, the rule for a series circuit is if we have 1 amp here, we have 1 amp everywhere. It's the same 1 amp. So I have 1 amp of current flowing through this resistance. If I have 1 amp of current flowing through a 1 ohm resistor, what do I get? I get 1 volt. This time it's going to be, I'm going to draw it over here just to get it away from there, positive to negative. Where the conventional current enters a resistor, it backs up and creates a voltage. It's like water going down a slow drain. We get a backup. So we get a higher voltage here and a lower voltage there. So the positive side is where conventional current enters the resistor, and the negative side is where it exits, positive to negative. So we have negative to positive, positive to negative. Now let's put our black probe of our voltmeter here and go along with our red probe and see what happens. Okay, so where's 0 volts? It's wherever you put the black lead. So you decide where 0 volts is. You put the black lead there and then measure with the red lead. I put the red lead where the black lead is. What do I have? I have no difference in voltage. The voltmeter measures the difference. No difference, 0 difference, 0 volts. So here I get 0 volts. Now let's put the red lead, let's get this out of the way, right there. So I've gone up 1 volt, negative to positive. I've increased by 1 volt, so I get positive 1 volt. Easy peasy. Now I'm going, let's put our little positive sign back here. I had to get it out of the way, but I just moved it. Now we're going to go further. We're going to go positive to negative. So we gained a volt, then we lose voltage. How much? 1 volt. So when I put my positive probe right here, I get what? I gained a volt, then I lost a volt. 0 volts. So that's why no matter where I put my meter around that loop, remember we can't separate these. We model them in series, but I cannot put a voltmeter between my voltage source and the resistance. I can only do it in this thought experiment to show that I gain a volt and lose a volt, but the truth is they're one entity. So across there, I both gain and lose a volt at the same time. Kind of boggles the mind, but that's obviously what's happening. So I go from here to here. I gain a volt or lose a volt, I have 0 volts. What happens when I go here? I gain a volt, and then I lose a volt. So I put my voltmeter here, 0 volts. I come over here, I gain a volt, then I lose a volt. 0 volts. Gain a volt, lose a volt, and I'm back to 0 volts. So I can put my voltmeter here, I get 0 volts. I put my voltmeter here and here, 0 volts. 0 volts. 0 volts. 0 volts. No matter where I put my voltmeter, remembering that I cannot probe between the resistor and its adjacent battery, I can only probe on the outsides, no matter where I put my voltmeter leads, I get 0 volts, which explains why, going back to our loop, once again, magnetic field inducing current in there, we have 10 volts of voltage, 10 ohms of resistance, so we have 1 amp of current, but I put my voltmeter here, or here, or here, or here. I'm going to draw this as a squiggly line to remind us that this is a resistor all along through there. And we've got, let me draw my current, 1 amp. So I've got 10 ohms of resistance, 10 volts, 1 amp, but no matter where I put my voltmeter, here and here, there and there, there and there, there and there, no matter where I put my voltmeter, what am I going to read? 0 volts, because every section I gain voltage, lose voltage, gain voltage, lose voltage. I can divide it into 10 pieces, I can divide it into 100 pieces, but in each piece I gain voltage, then I lose voltage. Well, you might say, well, that's nice and convenient. You have 1 volt, 1 ohm, numbers line up real nice, don't they? Well, let's go back and look at our experiment we did before here. Let's change the resistance. Let's make each of them 1/10 of an ohm. Now that'll mess it up, won't it? Okay, 1/10 of an ohm. Now it's not going to work, is it? Well, let's find out. We have 4 volts. 1, 2, 3, 4 volts total. How much resistance do we have? 0.1, 0.2, 0.3, 0.4. And that's going to give us 10 amps of current. So now I have 10 amps flowing in this loop. That's kind of high, isn't it? But hey, it's a thought experiment. We can have all the amps we want, don't we? So how much voltage am I going to have across this resistor now? Certainly I'm not going to get a whole volt, am I? Well, yeah, 10 amps through 0.1 ohms, 1 volt. So I cut my resistance by a factor of 10, but yet things still balance out that I get the same voltage across my resistance as the adjacent battery. As long as the batteries are equal and the resistances are equal, I am going to still get this same phenomenon. I can make these bigger, I can make them smaller. As long as they stay equal, I'm still going to get the same voltage across the resistor as I do across the battery, so it still works. And to prove this, I actually took a number of batteries and put them in a loop and showed, well, I'm not going to do too much here. I don't want to get too cluttered. Now a battery, of course, if we model a battery, I'm just going to draw one here. What is it? A battery consists of a voltage source. In this case, it was 1.5 volt AA batteries. And let's just say that there's, just to make things easy, 1.5 ohms of internal resistance. So that's our model for a battery. So a battery has built-in resistance, just like our wire does. So if this is true, what I've done here, if it is true, I should be able to take a number of batteries and put them in a loop, and as long as the batteries are the same, fresh batteries, same voltage, same brand, or whatever you need to do to make them the same, I should measure 0 volts around the loop. So what I did, and I'll demonstrate this in a second, I broke the loop, and let's put my black probe here, and then I put my red probe here. I'll stick with the 1 volts here for now so I don't have to redraw it. Got 1 volt, 2 volts, 3 volts. But then as soon as I closed the loop, I got 0 volts, 0 volts, 0 volts. So let's take a quick look at that video and you can see that this actually works out. Okay, ladies and gentlemen, here is the test. The question is, what happens if you put a number of batteries into a loop? And what I'm trying to find out here is if an application of Thevenin's theorem and Kirchhoff's voltage law works. And the theory is that when I have the loop broken, as you can see right here, I have no connection in the loop. As I move the red lead of this voltmeter to more and more positive sides of the battery, I should see a higher and higher voltage. However, with a proper application of Thevenin's theorem and Kirchhoff's voltage law, that whatever voltage I'm measuring with this open loop should go to 0 if I close the loop. I should get a 1.5 volts here, another 1.5 volts there, 1.5 volts, 1.5 volts, 1.5 volts, getting a total of 9 volts with these 6 batteries. But whatever voltage I'm measuring should go to 0 if I complete the loop. Let's go ahead and check the voltage here. I should see about 1.5 volts. 1.6, that's about right for a fresh alkaline battery. And here I should see twice that voltage, 3.2. And as I go around this loop, 4.8. This should be something over 6 volts, 6.4. There we have 8.0. I should now have something over 9 volts there. There we go, 9.6 volts. So it is done correctly. So what I'm going to do now is get this away from there because I just want to test points that are, that doesn't matter because it's going to be a loop here. But I'm going to clip lead these together and I'm going to measure across 2 of these batteries. So there we have 3.2 volts. That should go down to 0 volts. So I'm across 2 points of this loop, connect it, and voila! We went down to a negative voltage. As you saw, it went down to 0 volts. Why did it go negative? Because these are not perfect. My clip leads aren't perfect. My meter's not perfect. The batteries aren't perfect. And so I got something just a little bit off of 0, but I did prove that if you apply Thevenin's theorem and Kirchhoff's voltage law, there should be no voltage measurable anywhere around this loop when we have a closed loop. Let's just, for the fun of it, move this over to here. This is halfway around the loop. Let's get a connection here. So I should see about 4.7 volts. So now I'm halfway around the loop, and once again, when I connect this, boom, down to, yours makes no difference, 0 volts. So experiment proves the theory that no matter where I measure around in this loop, as long as it's a complete loop, I'm going to get 0 volts. Now let's go back to our loop of wire and take a look at a couple of scenarios. Here's our coil, here's our loop, and again I'm going to draw some squiggly lines on it to remind us that this has resistance. And once again we said that was 10 ohms, we'll stick with that. Total of 1 volt in the field, so there's 1 volt in the wire. Now I'm going to take a voltmeter and attach the black probe there and the red probe there. Now there are people who are saying that that you're going to get 2 different voltages depending on where you look at the voltmeter. So let's say we put 1 voltmeter over here and the other voltmeter, let's get rid of the probes here, just draw some lines. There's 1 voltmeter there. The other voltmeter is over here. Okay, so I have this voltmeter is between here and here, and this voltmeter is between there and there. And let's say, just looking at the numbers here, let's say let's say that, just to make things easy, let's say that I've got 1/4 of my loop here and 3/4 of my loop there. Does that look, that looks close enough. So if this is a total of 1 ohm, I should have a total of 10 ohms. I should have 7.5 ohms on this side, and I should have 2.5 ohms over on this side. So I have 1 amp of current. So 1 amp of current across 2.5 ohms. This should read 2.5 volts. And then this meter over here, measuring this part, should read 7.5 volts, equaling our full, that should be 10 volts, equaling our full 10 volts. So people say this is a paradox. You get two different voltages from the same place in the loop depending on how you look at the meters. What do you think about that? Am I going to measure a different voltage if I put the meter over here than if I put it over here? Well, yeah, I could, because look at my meter leads. They're being affected by that magnetic field, so I've got a problem here. What I need to do is make an apparatus where I can measure this, but not have my meter probes affected by the magnetic field. And a YouTuber by the name of From Jesse built an apparatus to do just this. Here's a picture of it. He calls it the Lewin clock. And so he has his probes going at a right angle to the magnetic field from the center so that he is not affected by the magnetic fields. So doing that and eliminating what would cause these to have different readings, now he has wires coming in like there and red probe over to here. Once again, perpendicular to the magnetic field so that it doesn't get affected by the magnetic field. And what are we going to read there? Do you remember? What am I going to read if I put my voltmeter here? How about here? How about there, there, anywhere? What am I going to read? 0 volts, because of what I already explained. Every section of this wire gains voltage and loses voltage at the same time. So if I break it into 10 pieces, I gain a volt, lose a volt, gain a volt, lose a volt. So no matter where I put my probes, I'm going to read 0 volts. So I am not going to read two different voltages unless I don't probe properly. I'm going to read 0 volts no matter where I put my probes. So the key to analyzing this is what? You have to put the resistance in this loop in series with the voltage. We can carry that to a slightly different level. This might be not as intuitive as what I just explained, but if I redraw my loop, once again, what do we have? 10 volts, 10 ohms, and therefore we have 1 amp of current. Okay, so I have 10 volts and 10 ohms. What do we have there? We have, well, remember that this loop is the secondary of a transformer, so why don't I draw it as that? There's the secondary of our transformer, and it makes a complete loop. But where does the resistance go? It has to go in series with the voltage. So let's put it right here. So here's our 10 volts. There's our 10 ohms. And we just have a regular circuit. In fact, I'm going to eliminate the coil there and just draw it as a battery. And what we have here is, let me erase this and redraw it. So we have a battery and a resistor, 10 volts, 10 ohms, and it just looks like any other circuit. We've just simply broken it down to the voltage in series with the resistance like a normal circuit. That's one way to analyze it. What we just did before, though, is we broke it down into, let's put some more batteries and more resistors. In this case, now we have 2.5 volts, 2.5 volts. Don't forget our resistors. Do I have them all in here now? Nope, we need one more right there. 2.5 volts, 2.5 volts, and 2.5 ohms, etc. So I just simply broke it into 4 pieces. We've broken it into 10 pieces. So we can break it up any way we want to, but the bottom line is we have 10 volts and 10 ohms. We can analyze that as simply 10 volts and 10 ohms. What's the key? The resistance goes in series with the voltage. Georg Ohm discovered that many, many years ago. And we can break it down into smaller pieces like we did before. I'll break it into a wedge where we have 1 volt and 1 ohm, and we have 10 of those, or we can have 100 where they're 0.1 volt and 0.1 ohm. We can break this down into multiple ways, but the whole idea is we break it down into a voltage source with a resistance in series, and then when we do that, we can properly analyze what's going on. So in review, let's just draw our final circuit here. There's our solenoid or coil. There's our loop of wire around it. And we have a changing magnetic field which is inducing a current in there. And what's the voltage going to be? What if I put my meter there? How about there or there or there? What am I going to read? 0 volts. Why? Because to analyze this, we have to break it up into its voltage and its resistance. 10 volts, 10 ohms, and we have to put those in series with each other. To fully understand why I measure 0 volts no matter where I put it, I simply broke this into 10 pieces. I'll just draw one here. 1 battery, 1 resistor, and we have 10 of those around there. Each is 1 volt and 1 ohm. As the current flows through, we gain a volt from here to here, negative to positive, but then we lose a volt, positive to negative, going there, and we do that every place around the circuit. So each of these entities is self-contained. We cannot probe in between the battery and the resistance. So I can only probe between the whole entities. So no matter where I put my meter, gain a volt, lose a volt, I always have 0 volts no matter where I look on the loop. So that is how voltage acts in a loop when we have uniform voltage and uniform resistance throughout the loop. So you might find people a little confused as I showed and think that you might be able to measure 2 different voltages, but actually no matter where you measure, it'll be 0 volts, and I explained why. And now you also see how to properly analyze a power source. So I hope you found this useful and informative. If you did, please give me a thumbs up down below, really helps the channel. And as always, a big thank you to my patrons. I could not do this without you, and thanks to everyone for watching.